Hello and welcome to my video, Anatomy of a Pattern of Very, Very Large Numbers. The numbers that we're going to look at today are numbers that increase both in base and exponentially, and the underlying pattern of how they increase, I think you'll be surprised when you see the actual pattern. I want to introduce the idea in stages just to give a sense of the proportion of these numbers, rather than just talk about, look at all these zeros. I'm going to start with a scenario. And let's imagine you can't have a good math problem without prisoners or people on an island. Let's imagine two prisoners are in adjacent cells and they can't talk to each other, but they do want to communicate. And so they're able to tap on the wall. So when they start communicating, they're going to communicate very simply. They're going to tap out 15 taps for an O or 26 taps for a Z, the most obvious pattern you can think of. And at a certain point, one of them gets an idea, and using the more laborious pattern, he introduces a simplified technique. He says to the other person, using his taps, make 3 boxes, draw them in the dirt, number them 1, 2, and 3, then for each box, divide it 3 by 3, and then each one will have a column 1, 2, 3, and then there will be rows 1, 2, and 3 across, and in each box put a letter of the alphabet. So with a total of 27 individual boxes, put a letter of the alphabet, and for the last one, that'll be the end of message. That'll mean the other person can talk. So in this, the most information that you need to convey would be 3 sets of 3, let's call them bits. So if you want to do a Z, you would go, and that means the third box, the second column, third row. So what you're doing is you're conveying a total of 27 possible pieces of information using up to 9 bits of information. Now, some of you know something about data communications. You're going to say, you know, those spaces between the taps also convey information, and so you're really looking at 11 bits, but we're not looking at it in those terms. So let's take a look at this visually using Excel. We can see that when you have 3 squared bits of information, you can convey a total of 27 pieces of information, which is 3 cubed. So the number 3 here represents the kind of additional, I'm going to say, dimension of information that you can convey. So if you have 2 squared bits of information, you can convey a column or a row. So you have 4 possibilities or 4 pieces of information. And here with 3 squared, you can convey the box number, the column number, and the row number. Now, if we move out and look at 4 squared, we're adding another dimension, another area of complexity. And so now we can have a column of boxes, a row of boxes, and then a column for each individual box within the larger box and 1 for the row. So for the total pieces of information, you have 4 to the 4th power. So each time we increase the base of the number we're dealing with. So 5 squared, which is 25, increases to 3,125 pieces of information, because this entire set of numbers here would increase by all these numbers, and you would get 5 columns and 5 rows, but you would also have that entire set of information multiplied 5 times out in a row, and with a 6, you would take all of that and increase it not only by column, but also by row, so the amount of information in each time increasing is increasing exponentially. So if we look at the square of the number compared to, if x squared is 25, then x to the x power is 3125. 6 squared is 36 to the 6th, which you can see 46,000. 7 to the 7th power is 823,000. And then we're moving up to 16,387,000,000, and then out to 10 billion. And you can see that these are increasing, but they're increasing at a kind of a steady rate. And so what is that steady rate that they're increasing by? And we don't need these examples any further. One thing to keep in mind, and it's central to the concept that we're looking at, is that each of these numbers is 10 to the 10th power in its own base. So this is 10 base 4 to the 10th power. This is 10 base 5 to the 10th power. So this number represents the ratio of this number over this number minus the ratio of this number over this number. And you can see that it isn't getting small very quickly or large very quickly. It seems like it's converging on a number, and the number that it converges on, you can't tell right at first, but when you realize that we're talking about numbers that are increasing by base, it's not too surprising to realize that we're starting to converge on a number that might start to get familiar, 2.718. And that is closing in on E, or Euler's number, or the base of the natural logarithm. Now, if you think about it, that makes sense. The base of the natural logarithm is involved in increasing numbers to 10 base some pattern. Now, we run into an issue with Excel here, and that's where we're going to start looking at this from a slightly different point of view, because Excel has a limitation, and there's even videos and Wikipedia articles on what happens to Excel because of the way it uses memory and floating points and all that, which we don't need to get into, but we can really only get up to 143 to the 143rd power to do our calculations. Anything over that, you start getting these errors. If we go to the Online Encyclopedia of Integer Sequences, one of the best websites out there if you like number patterns, the decimal expansion of E 2.71828, what comes after the 8 is a 1, 71828. Now in our calculations, we were coming up to 2.718287. So we're really not at E yet. And it's kind of remarkable how not close to E we are yet, considering how big the numbers are already. But what if we want to go and look into this further? We want to see how long it takes to approximate E. So let's try the Microsoft built-in scientific calculator. Okay, so using the scientific calculator, we can get to the 2,889 to the 2,889th power. And you can see that with the scientific notation, it's getting up to almost 10,000 places. So we can't really go further than that. 2890 to the 2890th power is going to be too much. You get an overflow. And that's because we're coming up on the limitation, but that's fine. So let's take 2889 to the 2889th power over minus this over its predecessor. And now look at our number here, 2.718. Let's put this up against the Online Encyclopedia. And how close are we now? 2.7182818. So from 143 to the 143rd power over its previous number, minus that previous ratio, up to almost 3,000 to the 3,000th power. I'm calculating with that, we've increased our accuracy or approximation to E. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. We've increased our approximation by about 3 or 4 decimal places. Now that's really nowhere near enough to suggest that we're really onto something. We've gotten more, we've gotten closer to E, but that's really, E is a very, very, very long number. Obviously it's infinite. You can see this is just, I don't know how many numbers they go out to, but this is what, like maybe 50 or so decimal places, a decimal expansion, and we're not even scratching the surface, and we're already at 3,000 to the 3,000th power. So how are we going to get any better of an approximation? Let's try a more powerful calculator. So this is called Kaizen on the Casio.com website. This is a very, very powerful calculator. We're going to see how far we can get using Kaizen. We're going to tell it to give us as many digits. So what actually is the largest number that we can get to with Kaizen? We're going to take this number here. So this is just shy of 14 million to the 14 millionth power. And this is going to be the largest number we're going to get to. And that is just like with the scientific calculator, they gave us an accuracy of up to 99.99. This is going to give us up to just one shy of 100 million places. So let's do our calculation using this number as our big number. And now how much closer we come to E? Now we're at 2.718281828459045. Oh, That's it. We haven't gotten that much closer, have we? One of the reasons why this is increasing so slowly, of course, is because you're taking one big number and its ratio over its previous number, and then you're subtracting it from that same ratio of the number previous to that, and you're only increasing each time by 2.718 something something. So, and that's a subtraction. And that's why this is moving so slowly. And yet the numbers are increasing by, again, by dimensions, by exponents. So to really nail this down would really require calculating power that I think right now they're probably using, to mine Bitcoin or critical line non-trivial zeros and all that kind of thing. So I think it may be that this using different bases may be a better way of looking at big numbers than our base 10 way of looking, where we just say, look at all these zeros. We're really not looking at really big numbers correctly, I think, when we do it that way. But that's just my opinion. Anyway, that's been this video, anatomy of a pattern of very, very large numbers. If you like it, please hit the like button and leave a comment. Thank you very much.